Today, we are going to learn a powerful approach to program design, solving simple problems like adding velocity to our SineSynth and multiplying streams. This method comes from the book How to Design Programs. It has helped me clarify my thoughts when tackling problems, and I hope it can help you too. This approach is called systematic program design, an iterative process for refining programs. It begins with 1. From problem analysis to data definitions. Here, we'll write down everything we know about the problem we want to solve, identify the information that needs to be represented, and decide how it will be represented in our chosen programming language. We'll formulate data definitions and illustrate them with examples. 2. Signature, purpose statement, and header. In this step, we state what kind of data the function will consume and produce. We'll also provide a concise explanation of what the function computes and define a stub that aligns with the signature. 3. Functional examples. Next, we'll work through examples that illustrate the function's purpose. 4. Function template. We'll translate the data definitions into an outline of the function. 5. Function definition. Now we fill in the gaps in the function template, using the purpose statement and examples to guide us. 6. Testing. We'll turn the examples into tests to ensure the function works as expected. Testing helps identify mistakes and clarifies the function for others reading the code in the future, something that will definitely come in handy for any serious program. 7. Refinement. Finally, we'll make improvements, making sure that all tests still pass. Let's begin with the stream multiplication problem. I chose this problem to start simple, and also because the multiplication of streams isn't always clear in the graph. By creating a dedicated processor for this task, we can visualize it more clearly. The task involves making the multiplication operation between two signals. Since we are working with the C major language, this operation will be performed by a processor. Imagine two signals, A and B, represented as sequences of samples, each with an index from 0 to n. The multiplication should be performed by multiplying the samples from both signals that have the same index. A0 multiplied by B0, A1 multiplied by B1, to A nth term, multiplied by B nth term. Understanding the problem. Multiplication. Inputs. Two numerical streams that represent signal amplitudes. Operation. Multiply the samples of these signals. Output. The result of the multiplication, which should then be passed to the output stream. Signature. The processor takes two stream inputs, likely floats, representing signal values, and outputs the product. Purpose statement. This processor multiplies two streams, in 1 and in 2, and outputs the result. Header or stub. Start with a main function calling advance, since it's required to compile that fulfills the signature, even if it doesn't yet compute anything. The input and output streams will be represented as sequences of floating point values. These examples will illustrate how the processor behaves over time for a small number of samples, e.g., for samples per stream. Example 1. The output stream out should be the element-wise product of the two input streams. Example 2. The output stream out should be. Now that we understand how the processor should behave, we can start implementing the actual multiplication logic. To do this, we'll simply use the multiplication operator asterisk between the two inputs and assign the result to the output using the left arrow operator. If we run the program, we'll notice there's no output. Actually, we might get one frame, and since it's mono, that would be a single sample with a value of 0. We can confirm this by logging the output. The multiplication is clearer now. To multiply streams, we need to perform a loop that multiplies each sample individually. Here's the complete definition of the processor, which reads values from the input streams, multiplies them, and outputs the result. You must have Cmajor command line tools installed. To set up the test, we will create a new folder called test inside the project. A file with the name of processor we want to test, .cmajortest, a folder inside of /test called golden data. A file inside the golden data folder should be named after the input endpoint. Since we are dealing with streams, I created two sine waveforms with different frequencies, in 1.wave and in 2.wave. For other endpoint types, we have different methods. Inside the mulstream.cmajortest, we put our processor, and at the top we call #run script, where frequency is the sample rate of the session. Block size specifies the maximum block size for the render. Samples to render, frames to render, sets how many frames to render. Subdirectory is the golden data location. Our test file will look like this. Now we use the command cmaj test path to cmajortest and test processor.cmajortest. This generates a new file. Expected output dash, name of output endpoint.wave. In this case, expected output out.wave, the console output. It is expected that on different architectures and with different optimization levels that the output streams may not match exactly across runs. This is due to differences in code generation, such as fused multiply add, used by the runtime on different processor and optimization combinations. Because of this, we do not expect output streams to exactly match the golden data. To solve this, the comparison with output stream values and the golden data uses the following algorithm. The maximum frame difference is calculated across the output frames. The largest absolute expected frame value is calculated. The dB of the max difference relative to the largest absolute value is calculated. This value is used to define how accurate the output is compared to the expected output. By default, the maximum accepted error is -100 dB, and this can be overridden by specifying the max diff dB value. Look for ways to improve the code to ensure it passes the test. This multiplication problem is simple, and it serves as a way to demonstrate an approach for solving more complex challenges. In this case, I believe there's nothing to improve, but feel free to tell me if I'm wrong in the comments. Final thoughts. This program design approach encourages you to dive deep into the tough problems you're working on, making it easier to find a solution. Another benefit is better code documentation. Difficult problems can be hard to grasp when you're relying solely on code and comments. Make this approach dynamic. While complex issues benefit from thorough documentation, simpler problems like this multiplication example don't require as much. Now let's apply this approach to add velocity to our synth. Problem analysis. Velocity values range from 0 to 127. In C major, we can normalize these values by dividing them by 127. But first, we need a way to retrieve these values. Velocity is a value that modifies the amplitude of a sound signal based on how hard a key is pressed on a MIDI controller, for example. In this case, the velocity will be multiplied with the signal generated by the oscillator, allowing us to control the volume dynamically. Understanding the problem. Inputs, MIDI notes, operation. Calculate the velocity value ranging from 0.0 to 1.0, which can be used to modulate the volume. Output, a 32-bit float value representing the velocity. Signature, purpose statement, and header. Signature, we will create a note velocity processor that takes in a note-on event and outputs a float representing the normalized velocity. Since the processor handles events, it doesn't require a main function to compile. Purpose statement. The note velocity processor extracts the velocity from MIDI notes, ranging from 0 to 127, and calculates the corresponding normalized float value. Header stub. We'll start with a stub to declare how the event input is processed. Functional examples. Example 1. Input. Expected output. Velocity out equals 0.787. Example 2. Input. Expected output. Velocity out equals 0.251. Function template and definition. It's a simple function. From the documentation, we see that the method getVelocity returns an integer between 0 and 127. To normalize it, we simply divide by 127. Tests. For testing, we need a way to pass a MIDI message as input in a JSON file. Fortunately, the JSON format is exactly what we need for testing. The message struct packs a 3-byte MIDI message into a 32-bit integer, arranging the bytes so that the message appears in the correct order when viewed in hexadecimal format. In a 3-byte MIDI message, the bytes represent: byte 1, status byte indicates the type of MIDI message, e.g., note on, note off, in the MIDI channel. Byte 2, data byte 1 typically represents the note number, e.g., 60C3. Byte 3, data byte 2 usually represents the velocity, intensity of the note or other parameters, depending on the message type. To generate the input file, we need the message and can log the following to the console. When we press C3 on the keyboard, the result will be. We can then reconstruct the message by taking the individual byte values and combining them into a single int32 MIDI message. This will recreate the full message from its byte components. When we call, we get. This is the format we need for MIDI in .json. The expected output in velocity out.json matches the functional examples. Refinement. Now we can make some improvements. Another method from the STD, MIDI, message struct get float velocity, could be used. In the previous SineSynth tutorial, the inputs from the voices are note on and note off events. So we can modify the input of the no velocity processor to receive note on events, for example, and access the velocity property directly. Now, these are the updated functional examples. Example 1, input, expected output. Example 2, input, expected output. For testing, use the following format in eventin.json. Now let's wire everything up. I'll place the develop processors folders inside our synth project. First, let's modify how we handle the multiplication of the ADSR and the oscillator. Now, the multiplication process is clearer. To apply velocity, we need another multiplication stream object and our note to velocity processor. Then, we use the output of the previous multiplication as input for this new one. The event in serves as the input for the velocity. Finally, we take the velocity output and use it as the input for the multiplication. In the next video, I'll show you how to generate a plugin by exporting the patch as a GIST project. Make sure to subscribe and hit the like button. I hope this tutorial was helpful to you in some way. See you next time.